Hello everyone and welcome to lecture 19 of computer architecture. Today we're going to talk about different ways that we address memory when we do control flow instructions, and we're also going to talk about how we address small data in memory. So last time we spoke about procedure calling. We said that a procedure needs space in memory to back up various things. If it needs to back up its own arguments and its return address, so a caller procedure needs to back up its own arguments and return address and temporaries before making a call so that it doesn't lose these values. A callee procedure needs to back up its caller's saved registers before it can use them for its own local variables. And we also said that if a procedure has many local variables, these variables may not be able to fit in registers, in the saved registers, so it would need to put them somewhere else. And we said that that somewhere else is a stack. There's this notion of a stack in memory where procedures put their data. And we went on to talk about how memory is laid out. We saw how memory is laid out into different segments. We have the reserved segment for the operating system, the text segment for the instructions, the static data segment for global variables, and then over here we have the dynamic data, or the heap, that grows from a low address to a high address, and then we have the stack that grows from the high address to a low address. And we said that every time a procedure calls another procedure, what happens is that a stack frame is allocated for the new procedure, and the stack frame is going to contain things like the procedure's saved arguments and return address. If that procedure is going to call another procedure in the future, it's going to store some of the saved variables of the caller if the procedure needs to use the saved variables for something else, and things like local arrays and structures. And we said that we're only going to use the stack pointer in this course because we're going to assume that we will only allocate and deallocate from the stack when we enter and exit a procedure. In practice, you can allocate and deallocate on the stack during the procedure execution, and that's why we would have a frame point, both a frame pointer and a stack pointer. A frame pointer is fixed during the procedure duration, and we can use it to access things on the stack, and then the stack pointer is used to allocate and deallocate things from the stack. We then moved on to look at code examples of how we can write MIPS code for functions where we observe the calling conventions that we talked about. We started with this leaf example that took a bunch of arguments and had a local variable, and then did some computation and returned the result. And we generated code for it, and we saw how we need to save S0 on the stack, so we need to do some stack allocation. And then we do the operations that we want, and we find our parameters inside of the A registers. And we saw how we put our final result in the V register for the caller to be able to find it. And then we deallocate the stack and use jump register to return to the caller. We then looked at a more complex example where the procedure was calling other procedures. And we saw how when a procedure calls other procedures, it needs to back up its own argument and return address registers so that it doesn't lose them. And we saw how we generated code for this. Again, first thing we do when we enter is we allocate and save our arguments and return address to the stack. And then we do the operations that we want to do. We find our parameters in the A registers. We put the final result in the V registers. And of course, before we turn, we need to deallocate the stack. So this was the if branch, and this was the else branch. And the else branch was performing a function call. So we saw how we did jump and link to do the function call. And we saw how after we return from the function call, we need to restore the argument and the return address registers because doing the function call loses these values for us. Okay, so this was a brief overview of what we covered last time. Any questions about last time's material? Okay, if there are no questions, then let's move on to today's material where we're going to talk about memory addressing and small data. So how to access data that is less than one word, and also how to represent memory addresses inside of control flow instructions. Okay, let's start with branch addressing. So we've seen before how to represent various instructions as 32-bit words. We took a look at arithmetic instructions. We took a look at load and store instructions. And now what we want to do is we want to look at branch instructions and see how I can represent a branch instruction as a 32-bit word. Now, what does a branch instruction need? Well, the branch instructions, remember, we have branch equal, branch not equal. They take two registers and a label that represents the target address. Okay, so we have two registers and we have a label that we need to represent. So what seems to be a good format for this kind of representation? Do you think it's the R format or the I format? I format, exactly. So the R format takes three registers. The I format, the R format takes three registers. The I format takes two registers and some offset or address or whatever. So here for the branch instructions, since the branch instruction takes two registers and a label, then what we will do is we will represent it using the I format, where we have the opcode for the branch instruction. RS and RT will be the two registers that we're comparing if they're equal or if they're not equal. And then the remaining bits are going to be the constant or the address. So somehow we need to represent our label as 16 bits. Okay, so the I format supports 16 bits. However, the addresses that we need to branch to are 32 bits, right? So an instruction is stored at some memory address. This memory address is going to be 32 bits long. So the question is, how can we use 16 bits to represent a label when the label refers to a 32-bit address? So how can we use 16 bits to represent a 32-bit address? Well, the answer is we're going to do the following. First, we observe that most branch targets are nearby, right? When we branch, we usually branch to a nearby instruction, right? Because branches usually come from either having some kind of if statement or some kind of loop, where we have a condition, and based on this condition, we want to go to some instruction. Okay, so because of that, since branch targets are close by, we're going to be able to take advantage of this to represent the branch target using less than 32 bits. The other observation is that instruction addresses are multiples of 4. Okay, so even though an address is 32 bits, an instruction is 4 bytes. So the address of an instruction is always going to be a multiple of 4, right? Because we have an instruction at address 0, an instruction at address 4, instruction at address 8, but we're not going to have an instruction at address 3, for example, because instructions are 4 bytes. So we will also take advantage of this observation to say, okay, hey, the last 2 bits of the address are not useful. They will always be 0, 0 because the instruction is a multiple of 4. So taking advantage of these two observations, what we're going to do is we're going to use something called PC relative addressing. What does that mean? It means that rather than representing the address of the label as kind of a 32-bit address, rather than storing that 32-bit address in these 16 bits, what we're going to do is we're going to store an offset in these 16 bits that is going to be an offset from the current PC, the current program counter. In other words, rather than storing a 32-bit address here, we're going to store how far away the instruction that we're branching to is from the branch instruction itself, from the current branch instruction. Okay, so in summary, the target address is going to be the PC. The PC is the program counter. It points to the current instruction. In this case, the current instruction is the branch instruction. Okay, so the target address is going to be PC plus 4. Where this plus 4 comes, you guys will see later. But basically, when we're executing instruction, the program counter has already been incremented by 4. So the target address is going to be PC plus 4. Okay, and then plus we're going to add the offset that we stored over here times 4. Why times 4? Because the actual offset is always going to be a multiple of 4 because instructions are always stored at multiples of 4. So rather than you only storing 4, 8, 12, 16, 20, 24 over here, we'll just store that a value that is that value divided by 4 and then multiply it by 4 to calculate the offset. Okay, so then the target address is going to be PC plus 4 plus the offset times 4. And then the offset over here is the value that I will store in these 16 bits. Okay, so I will store a 16-bit offset. And then when I execute the branch instruction, the target address of the branch instruction can be found by multiplying the offset by 4 and adding it to the program counter plus 4. Okay, let's do an example to make this more clear. Let's say we had this code over here. This is a loop. So we have, some, condition over here. We load, we branch based on the value. Then we add, and then we jump back to the loop. Okay, so here, this branch is going to exit the loop if some condition holds. In this case, we're checking if T0 is not equal to S5. And if the condition does hold, we're going to continue here, and then we're going to jump back to the loop. So what we're interested here specifically is we're interested in this branch instruction over here. We're interested in branch not equal T0 S5 exit. And the question is, how do we, by the way, over here to the left, I'm showing the address that each of these instructions is stored at. Okay. So the branch not equal instruction is stored at this address over here. I'm representing the address in hexadecimal. Okay, and the exit label refers to the instruction at this location over here, which is this address over here to the left. Okay, so the question is, how can we represent this this branch not equal instruction as a 32-bit value? And let's see how to do that. So first, we said that the branch instruction is going to follow the I format. So we have an opcode. We have RS and RT, the source and the two source registers, and we have this constant address which we're going to use to represent exit. So first of all, what is the opcode going to be? Well, the opcode corresponds to whatever instruction we are executing. So in this case, the instruction is the branch not equal instruction. So we're going to have the opcode for branch not equal. Okay. What about RS and RT? What are RS and RT going to be in this case? Right, so the RS and RT are going to be T0 and S5. So RS will be T0, RT will be S5. And then the constant or address, the label is going to be the exit label. Okay, so these are the values that we want to represent in each of these fields. Okay, now what we want to do is we want to convert these to the actual numbers that will be stored. So for branch not equal, we need to look up the opcode. So we're going to go to this to the MIPS reference sheet, and we're going to look up the opcode. So we look for a branch not equal. We find that it's over here, right? It's using the I format, so it's not going to have a func field. It's just going to be an opcode. So the branch not equal opcode, the opcode for branch not equal is going to be 5. Okay, so we come back here and we say this is 5 over here. Okay, then we need to represent T0 and S5 as numbers. So we're going to go to our table up here. We're going to look up T0. Well, T0 is 8, and S0 is 16, so S5 is going to be 21. Okay, so we come here and we store 8 and 21. Okay, and then finally, which is what we care most about today, is how do we represent this exit label? How can you represent this exit label as a 16-bit value? Well, let's review what we said. We said that to represent this value, we're going to use PC relative addressing. And PC relative addressing says that the target address, in other words, this address of the exit label, is going to be PC plus 4 plus the offset times 4. So the PC is the program counter for the branch not equal instruction, right? So I have the target address and I have PC plus 4. And what I need to do is I need to find now the offset. Okay, so I plug in the target address, it's this value over here. I plug in the PC, it's this value over here. Okay, and then I subtract this value over. So I'm going to be left with C in hexadecimal, which is 12 in decimal. And then I subtract 4, that leaves me with 8 in decimal. And then I divide 8 by 4, and that leaves me with the offset being equal to 2. Okay, this is just simple arithmetic. You can do that on your own. Okay, so the offset is 2. So what I will store in this value is 2. Okay, and the way that I recover the target address from this value 2 is I multiply 2 by 4 and then I add it to the PC plus 4, and that's how I get the target address. Okay, and then you can go on and convert these values to the corresponding binary values. You guys know how to do that, so I'm not going to do that. But what's most interesting today is how we get 2 as a way to represent the exit label for this code over here. Okay, is it clear? Does anyone have any questions? So someone's asking, what if the target address was far from the branching address? So that's very uncommon. And the reason is that branches usually come from loops and if statements. So you would need to have a loop that's larger than that. You need to have an offset that's larger than 2 to the power 15. And 2 to the power 15 is a very big number. So imagine that your loop was 2 to the power 15 different instructions. Thousands of instructions. That's very uncommon. However, there is a way around it if we, for some reason, need to branch that far, and I will talk about that in a few slides. Okay, so hold that question for a few slides. Right, so that's a very good observation. So this constant, just like with load instructions, the offset is a signed value, and it can be a positive or negative value. If it's a negative value, it's a 2's complement. It's the same thing for these branch instructions. For the branch instruction, this offset over here is a signed number. And what that means is that the offset could be a negative number. Okay, and if it was a negative number, it would be represented using 2's complement. So the 16-bit value that represents the constant or the address, this is a 2's complement value, and it can be a negative number, just like it was for the load and store instruction. Okay, it's a very good question. Okay, if there aren't any other questions, let's move on to the next control flow instruction, which is jumps. So the other question is, how do we do jump addressing? How do we represent jump instructions? So for the jump instruction, the J, and by jump instruction, I'm specifically referring to J and JAL, not jump register, because jump register, you're just jumping to an address in a register. A register can store 32 bits, so we don't have to worry about jump register. But for jump and link, the target of jump or jump and link can be anywhere in the text segment. It can be anywhere in the code. So the 16 bits that we use for the branch instruction are most likely not going to be enough for the jump instruction. So in order to represent jump instructions, we actually have a third format, which is the J format. Okay, so we saw the R format and the I format before. Our third format is the J format, and the J format is used for jump and link instructions. The J format looks as follows. You have the 6 bits of opcode. This is the same as the R and the I format. All 3 formats have a 6-bit opcode. But then the J format is not going to have any registers because the jump doesn't take any registers. It's going to dedicate all the remaining 26 bits to the address. Okay? So we have 26 bits to represent the address. Now we still have a problem here because the J format supports 26 bits, but addresses are 32 bits. So the question remains, how are we going to represent a 32-bit address using just 26 bits? Okay, well, we're going to make the following observations. We're going to use a technique called pseudo-direct jump addressing. This is based on the following observations. First, the instructions are always multiples of 4. Again, we took advantage of this with branch instructions. We're also going to take advantage of it here. The instruction addresses are always a multiple of 4. Okay, so even though they're 32-bit words, we know that the lower 2 bits are always 0 and 0. So we don't need to represent these lower 2 bits. We only need to represent the 30 bits, and then we can multiply those 30 bits by 4. Okay, so 30 bits is all we need to represent, but we still have a problem, which is that we only have 26 bits, right? We need 30 bits to represent the address, and then we multiply it by 4 to make it 32 bits. However, the problem is that we only have 26 bits. So we have 4 bits that we cannot represent from these 30 bits. So what we're going to do is we're not going to represent the most significant 4 bits. Instead, we're going to take those from the PC. So we're going to get the remaining upper bits from the program counter. Okay, so with pseudo-direct jump addressing, the target address is found as follows. We have the target address is going to be equal to the most significant 4 bits of the program counter concatenated with the address, which is 26 bits, times 4, that makes it a 28-bit number. Okay, so we're going to get 4 bits from the program counter, and then the address is going to be 26 bits times 4, that makes it 28 bits. Okay, and this is how we get 32 bits from the 26 bits that are represented in the jump format. And this technique is called pseudo-direct jump addressing. And the intuition here is that even though we might need to jump to a place that's very far away, it's very unlikely that we need to jump far enough such that the top 4 bits of the PC change. Okay, the top 4 bits of the PC means that the distance we're jumping, if the top 4 bits of the PC between the jump instruction and the label we're jumping to are different, it means that we're jumping to a place that is 2 to the power 28 away. So we're looking at a program that is 256 megabytes in size. Okay, and that is very uncommon. And although it's uncommon, just in case it does happen, there is also a way to deal with it, and we will talk about that later. But for now, let's do an example to make this more clear. So let's say back to this example over here, but this time I would like to represent this jump instruction over here. I want to represent jump loop. Okay, so the jump instruction has the following program counter. Okay, and the loop label needs to point to this address over here. Okay, so how do we represent the loop label? Well, first of all, we're going to use the J format to represent the instruction. The J format is going to have 2 parts: the opcode and the 26 bits for the constant or the address, or the label in this case. And the opcode is going to be the opcode of J, the J instruction, and then the constant or address in this case are going to be whatever we're going to use to represent loop. So here we need some way to represent the loop label. Okay. Now let's get the corresponding numbers. So what is J? Well, I go to my table and I look up J. So here, this is the table, and J in the table is over here, which corresponds to the decimal value 2. So the opcode for J is going to be 2. And then the loop label, we said we're going to use pseudo-direct jump addressing to represent it. What does that mean? It means that the target address, which is this value here, is going to be equal to PC, the top 4 bits of the PC, so bits 31 to 28 of the PC, concatenated with the address times 4. This address is the value that we are storing in this field over here, the 26-bit value. Okay, what that means is that this value in green here, 1408000, again, I'm using hexadecimal, needs to be equal to the top 4 bits of the PC. What are the most significant 4 bits of the PC? Well, every hexadecimal digit is 4 bits, right? So here, this 1 digit over here is going to be the top 4 bits. Okay, and then concatenated with the address times 4. Okay, so what do I do? Well, I remove the 1 from here and then remove the 1 from here, which means address times 4 needs to be 408000 in hexadecimal. And then I divide that by 4, and I get the address is 102000 in hexadecimal. Okay, so the value that I will store over here is 102000 in hexadecimal, and you can figure out what that corresponding value is in binary or decimal, whatever you care about. Okay, so here this 2 is in decimal, and then this here I'm representing it in hexadecimal just for convenience. Okay, and you know how to convert this to binary. We have seen that before. Okay, so this is how you represent addressees in the J format. Any questions about the J format? Okay, well, now we get to the topic that one of your colleagues was asking about, which is what if we need to branch far away? What if we need to branch somewhere that is farther away from the what we can represent using the 16 bits? Okay, so if the branch target is too far to encode with the 16-bit offset, what we're gonna do is we're gonna rewrite the code using a jump instruction. How do we do that? Well, if we had this code over here, well, we have branch if equal S0, S1 to L1, and L1 is very far away. And then if we don't branch, we just go on and execute this next instruction over here. Doesn't matter what it is. What we will do instead is we of course we keep L1 far away. We don't change L1. But what we're going to do is we're going to take this next instruction and we're going to put a label on it, and we're going to label it L2. Okay. And then rather than branching to L1, what we're going to do is we're going to flip the branch instruction. So rather than if on equality branching to L1, we're going to branch to L2 if they are not equal. Okay, so we're going to write branch not equal S0, S1 to L2. So if they're not equal, we're going to go to L2. And if they are equal, we're going to go on to execute the next instruction, and the next instruction is going to be jump L1. Okay. So by playing this trick, we were able to branch to somewhere far away by converting the branch to something far away into a branch to the next instruction, which is closer, and otherwise jumping to the label that is far away. Okay, so this is how we can convert code that branches far away to code that branches nearby, and then using the jump to go to the label that's far away. All right, any questions about this technique? Okay, well, this covers branching far away. What if we want to jump far away? So what if the jump target is too far to encode with a 26-bit address? What we can do is we can rewrite the code using jump register. Okay, so if we saw the limitation of pseudo-direct jump addressing is that the top 4 bits of the program counter and the target address have to be the same. And then this gives us a range of around 256 megabytes. But if for whatever reason we want to jump even farther than that, we can rewrite the code to use jump register, because jump register takes a register, and that register can store a full 32-bit address. So if I have this code over here, jump to L1, where L1 is far away, and then I have this kind of instruction that comes after. What we can do is, rather than having jump L1 like this, if L1 cannot be represented using a jump instruction, what we can do is, we keep L1, we have the code that comes after the jump instruction. What we will do is we will put L1 in some register. It can be any register. Here we're going to just use T0 because it's a temporary value. We don't need it later on. Okay, and then we're going to use jump register to T0. Okay, so L1 is a 32-bit constant now. We're going to put this 32-bit constant in a register, and then we'll do jump register T0. Okay, so this is how we can jump to a place that is very far away. Now there's one problem over here, and that problem is, how do we put L1 in T0? So L1 is a 32-bit constant, right? The address of an instruction is constant because the instructions don't move around in memory. They're always in the same place. So how can I put a 32-bit constant in a register? Okay, we've seen before that if we have 16-bit constants, we can deal with those using the immediate instructions. So we can create 16-bit constants from immediate instructions, but we don't have a way to create 32-bit constants. So what can we do? What do you think we can do? Well, not 26 bits, right? Because 26 bits is a jump instruction. We cannot create a 26-bit value. We can represent a 26-bit value in jump instruction. We can create a 16-bit value. So your observation is correct, which is that we can create a 16-bit value and shift it, and then add another 16 bits. Exactly, we can do that. And there's actually an even more efficient way of doing that. So if you want to represent a 32-bit constant, what we can do is, again, most constants are 16 bits, are small, so 16 bits immediate are sufficient. But in the rare case where we want a 32-bit constant, there's actually an instruction that helps us do that. So rather than creating a 16-bit constant, shifting it, then adding another 16-bit constant, we already have an instruction called load upper immediate that loads or that creates a 16-bit constant in the upper half of the word. Okay, so load upper immediate, it takes a register RT and it takes a constant, a 16-bit constant, and it puts the, you can probably guess that this is represented using the I format. It puts the 16-bit constant in the left part of the word, and it clears the right part of the word. So for example, if I do a load upper immediate S061, so what it will do is it will put the binary value of 61 in the upper part of the word, the left part of the word. And now what I need to do is I need to then have another instruction that initializes the right, the 16 bits on the right. What can I do to initialize these? Remember, we said before, how do we set specific bits inside of a register? Right, we're going to have some mask, and the instruction that does that masking is the OR instruction. So we're going to use OR immediate to we're going to combine the load upper immediate with OR immediate to set the remaining 16 bits. So if we do OR immediate S0 S0 and then give it some value, it will set the lower 16 bits to the binary value of whatever value we give. Okay, so if we would like to create a 32-bit constant, we do that by combining load upper immediate and OR immediate. Load upper immediate initializes the top 16 bits, and OR immediate initializes the bottom 16 bits. Okay, so if we want to jump to a 32-bit address, we can use load upper immediate and OR immediate to initialize the value of that address in some register, and then use jump register. Okay, any questions about this? Is it clear to everyone? Oh, so someone's asking, how do we make sure that the right part of S0 is 0? So the load upper immediate instruction behaves that way. The load upper immediate instruction will set the top 16 bits to the whatever value you give it, and it will clear the remaining 16 bits. So the load upper immediate will set these remaining bits to 0. Okay. Okay, someone's asking me if I can repeat. What part of it would you like me to repeat? The OR immediate. So remember, we spoke before about what I would like to do is I would like to initialize, I would like to kind of set these lower 16 bits over here. So we saw before how if we would like to set specific bits inside of a word, we can use the OR operation. So OR immediate will take S0 and it will OR it with some value over here. So to set these lower 16 bits, I just provide the value that I would like to that I'd like to set over here as an immediate operand to the OR instruction. And what that will do is that when you OR the 16 bits with this constant, the result will just be the constant, because anything OR 0 will be whatever that thing was. Okay. Okay, so we now saw how to represent the 60, how to represent branch instructions in binary. We saw how to represent jump instructions in binary, and we saw how we can branch and jump to locations that are farther away than what the branch and the jump instructions support. And we saw how we can create 32-bit constants in the rare case that we want very large constants that are larger than 16 bits. Okay. Next, what we're going to talk about is we're going to talk about representing small data. Okay, we're going to talk about representing small data. And what do I mean by small data? Well, so far we've been dealing with integers. We've been dealing with 32-bit words, but some data that we'd like to deal with can be smaller than words. So, for example, characters. You know, when you write program with characters, characters are smaller than words. There are different kinds of characters. The most common representation of characters is the ASCII format. ASCII is a set of 128 characters, and to represent 128 characters, we need 8 bits or 1 byte. Okay, so we need 1 byte to represent ASCII characters. So when, for example, if you're writing a program and you write car or char, and you provide kind of a string of characters, each of those characters is going to be 1 byte. It's not going to be an integer. Okay, so if I want to deal with these individual bytes, okay, I cannot use I have to do something special. There's also Unicode. So Unicode is another representation for characters, and this includes an expanded set, which includes different characters from different languages and certain symbols and things like that. And by default, Unicode uses 16 bits or 2 bytes or 1/2 word. So a word is 4 bytes. So we usually refer to 2 bytes as a half word. Okay. So our program might want to operate on ASCII characters on individual bytes, and our program might want to operate on Unicode characters or half words. And the question is how to do that. Well, we need a way to be able to load and store data that is smaller than 1 word. And one way to do this we could use bitwise operations. So I could load a word, and that word contains 4 bytes, but I only care about one of those bytes. So I can shift and clear. I can shift certain bits and clear other bits in order to isolate that byte. So that's one way to do it. But the problem is that this requires multiple instructions, and processing characters is something that we do very frequently. So we'd like to do that fast. So in the spirit of making the common case fast, string processing or processing characters is a common case. So we would like to have special instructions to be able to deal with individual bytes or deal with individual half words. So what we're going to do is we're going to have byte and half word operations, and these will look as follows. So MIPS has byte and half word load and store instructions. Okay. We have load byte. LB is instruction that does load byte. So remember, our load instruction, the one we first introduced, was LW, and what that means is load word. Okay, well, what we have is we have LB, which is load byte, and we have LH, which is load half word. Okay, now since a byte is the address of a byte is a multiple of 1, right? A byte can be anywhere in memory. The offset here is can be any value, any multiple of 1. Remember, with load word, the offset had to be a multiple of 4 because the words were 4 bytes long. Well, with load byte, the offset can be any value. It has to be a multiple of 1 because the bytes are 1 byte long. Okay. And similarly, load half word, the offset is a multiple of 2 because a half word is 2 bytes long. All right. So we have load byte and load half word. Okay. And in fact, we also have, this is something we didn't have with load word, we have load byte unsigned and load half word unsigned. Okay. And again, here the offset can be any value. Here the offset is a multiple of 2. But the reason that we have 2 versions of load byte, load half word, and load byte unsigned, load half word unsigned, is because when we load a byte, we're taking an 8-bit value and we're storing it in a 32-bit register. And when we take an 8-bit value and store it in a 32-bit register, what we need to do is we need to fill the remaining bits, right? We have 8 bits that we loaded, but we have 24 bits that we need to fill. And the question is, what do we fill those bits with? Now, if the value that we loaded was an unsigned value, right? Because it might be a character, but it might also be an 8-bit integer, right? Because these processors support handling 8-bit integers. So if the 8-bit value that we loaded was an unsigned value, we just want to put zeros to the left, okay? However, if the 8-bit value that we loaded was a signed integer, was a signed 8-bit integer, then the values we can't just add zeros to the left, because if the value was negative, if the leftmost bit was 1, adding zeros to the left will convert our negative 8-bit integer into a positive 32-bit integer, which is not what we want. Okay, what we want is we want to take our negative 8-bit integer and convert it to a negative 32-bit integer. So load byte will do sign extension. If the leftmost bit is 0, it'll fill it up with zeros. If the leftmost bit is 1, it'll fill it up with ones. Whereas load byte unsigned will always do 0 extension. It'll always fill the leftmost bits with 0. Okay, so load byte will do sign extension. Okay, and load byte unsigned will always do 0 extension. Load byte unsigned will fill the remaining bits with 0, whereas load byte signed will fill the remaining bits with whatever the leftmost bit was, so that if it was a negative number, it remains a negative number in 2's complement. Okay. All right, so we have load byte, we have load byte unsigned, we have load half word, we have load half word unsigned. We also have store byte and store half word. Okay, and store byte and store half word will store the rightmost byte or half word in the register. Okay, now we don't need store byte and store byte unsigned, because here we're truncating, we're not extending. So we're removing bits, we're not adding bits. So we don't care about whether the bits we're going to add are zeros or ones, because we're not adding bits. Okay, so these are the 3 instructions, 3 special instructions for dealing with individual bytes and individual half words: load, load unsigned, and store. And as an example of how we use these instructions, let's do kind of a code example. So let's say we had some code that processes a string, okay? And what this code is going to do is it's going to do if x0 is not equal x1, x1 equals s0. So what the code is doing is it's checking the first 2 characters in the string, okay? And if the 2 characters are not the same, it's going to set the second character to be equal to the first character. Okay, so I'm going to take a string and I'm going to make sure that the first 2 characters are the same. Okay, it's not a very useful program, but I'm just using it here for demonstration purposes. Okay, and let's say that x is a character array. So here x in this case is an array of characters, so an array of bytes, and the address of x is stored in the register S0. Okay, how do I generate the corresponding MIPS code for this? What should I do? What's the first thing I do over here? Right, the first thing I need to do is, obviously I need to compare x of 0 and x of 1, but before I do that, I need to load these values, right? So the first thing I do is I need to load x0. Well, x is a character array, so x of 0 is a byte. So what we're going to do is we're going to do load byte, and the byte, since this is a character, I'm not processing integers, I'm processing characters, so characters are like unsigned integers. Okay, so we're going to use load byte unsigned. So the first thing we will do is we'll do load byte unsigned. Okay, and the base register is x, so it's going to be S0, and the offset is 0. So we're going to do load byte unsigned. We're going to access it from 0 of S0. Okay, and we're going to save the value we loaded in a temporary register. So we're going to load x of 0 to T0. Okay. What do we do next? Next, we want to load x of 1. How do you load x of 1? So it's going to be the same thing. We're going to use load byte unsigned, but this time the offset is going to be 1. And notice an important thing here is that before, when we did, for example, we had an array of integers and we did a of 1, the array of that 1 became an offset of 4 because it was an array of words. Okay, so the offset was 4 because the word at offset 1 corresponds to the 4 bytes away from the base register. However, in this case, since this is an array of characters or an array of bytes, an offset of 1 will correspond to an offset of 1 in the instruction. Okay, so now we've loaded x0 to t0 and we've loaded x1 to t1. Okay, what do we need to do now? We need to compare them, right? So if they are not equal, we're just going to continue to execute the next instruction. If they are equal, we're going to branch and skip the body of the if. So we're going to use branch if equal t0 and t1. So we're going to branch if equal t0 and t1. And if they're equal, we're going to skip over to a label L1 that is after the body of the if statement. If they are not equal, then we're going to move on to execute the body of the if statement. And now how do we do x of 1 is equal to x of 0? Okay, well, I'm going to do an optimization here. We already loaded x of 0, so we're not going to load it again. X of 0 is available inside of t0. So now what do we do next? We want to do x of 1 is equal to t0. How do we do that? Right, we're going to use the store byte instruction. So we're going to do store byte, and what are going to be the arguments to store byte? We're going to store the byte in t0, and where are we going to store it? We're going to store it in x of 1, which is going to be 1 of s0. Okay, so we're going to do store byte t0 in 1 of s0. Okay. And with that, this covers the topic of loading and storing bytes. Any question about loading and storing bytes? Okay, if there are no questions, then that is all for today. You can read more about what we covered today in sections 2.9 and 2.10 of the textbook. And that is all for today. I will see you next time. Bye, everyone.